Welcome back to this course, Econometrics. Today we'll be looking at multiple linear regression, the continuation from the last module. By way of module objectives, by the end of this module, students should be able to explain why multiple regression is needed now and how it extends simple regression. Students should be able to state the multiple linear regression model and interpret its components. Students should be able to derive and compute the OLS estimator in multiple regression and explain the key assumptions for unbiasedness. Students should be able to interpret coefficients as partial effects and distinguish statistical significance from economic significance. Students should be able to detect multicollinearity using correlation patterns and variance inflation factors, explain its consequence, and apply solutions. Students should be able to compare models using AIC and BIC and understand the trade-off between fit and complexity. Students should be able to correctly incorporate dummy variables and interaction terms and interpret them in economic terms. Students should be able to write and present multiple regression results clearly with appropriate diagnostics and caveats. By way of introduction, multiple linear regression is a regression framework that explains one dependent outcome using two or more independent or explanatory variables. In module 2, we studied XLR, which is simple linear regression, where one predictor X explain why. SLRO is valuable, but most economic outcomes have multiple dependents. For example, wage depend on education and experience. Demand depends on price and income. Investment depend on interest rate and expected output growth. If we ignore relevant variables, the estimated effect of the included variable may be biased because it will absorb some of the influence of omitted factors. MLRO addresses this by including several predictors in the same module. Enable us to estimate partial effects. This improves realism, supports better prediction, and help reduce omitted bias. However, MLRO introduces new issues such as multicollinearity, high correlation among regressors, and the need for model selection, that is choosing a usable parsimonious set of predictors. OL MLRO requires careful handling of categorical variables such as gender or region and interaction effects, that is situations where the impact of one variable depends on another. Let's look at some of the key terms. I've already checked it before. Dependent variable, the outcome of the predict. Independent variable, eccentric factors that account for y. Parameter, this is the true quantity that measures an aligned economic relationship. An estimator, this is the formula that uses sample data to estimate the B, that is the beta. Error term, they are all influences that are not accounted for in the module, e.g. omitted variables. Why ceteris paribus effect? The effect of changing one x while holding other x's variable constant. This holding constant interpretation is exactly what economists often mean by comparative statics. Another name for this is comparative statics. Now, this is the multiple linear regression model. This is population at the top. This is population here. This is how it's measured here. Why this is sample. As you can see, there's more than one x that is affecting y, right? For simple, it was just one. But for multiple, you can see there's x1, there's x2, up to x infinity. K here represents infinity. For sample, you can see the difference here, right? The beta is a smaller beta, right? And in population, B0, B1 are fixed. In population modeling, the first equation, they are fixed but unknown. They define the systematic component of y, giving x 1 to sk infinity. The error term contains omitted determination, error, and all of that. While in the sample, we replace unknown betas with estimated computed from data. So we take from that large population a little bit and estimate the beta. The fitted value, which is y, is the model prediction of y, given the observed x value. So you can see it's now this. Crucial interpretation, B J measures the effect of xj on y, holding the other x variables fixed. This is the defining advantage of multiple regression over simple regression. Now let's look at what does holding other variables constant really mean? Like I said before, I will just explain it better now. In multiple regression, we interpret Bj as a partial flow. Bj can be any, 1 or 2 or 3. How y changes when xj increases by 1 unit, while the other variables remain unchanged. This matters because many predictors are correlated in real life. Education and experience may move together. Income and consumption are strongly related. Price and advertisement can move together. Without holding other factors constant, a simple relationship can miss several effects. Practically, multiple regression isolates the unique variation in xj that is not shared with other regressors and uses that independent variation to estimate the partial effects. Let's look at matrix notation. Why economists use it? This is the model. Let y be any n times x vector of atoms. Let x be n times k plus 1 matrix containing a column of y's for the intercepts and k columns of regressors. Let b1 be k1 plus 1 times vector of the parameters. Matrix notation is compact and makes derivations cleaner. It also matches how softwares compute regression. Most advanced economic results are easiest to express using matrices. Let's look at some of the classical OLS assumptions in multiple regression. The assumptions are similar to SLR, but are now conditions on all regressors jointly. We need them for unbiased estimation and valid inferences. The key assumption is that there's linearity in parameters, just like SLR. There's random sampling. There's no perfect multicollinearity. There's zero conditional mean. There is exogeneity. There's homoscedasticity for unusual standard errors, and there's no autocorrelation, especially in time series. In practice, violations can change what is reliable. Some violations affect standard errors and hypothesis testing. Others affect coefficients themselves. Let's look at partial effects. That is using concrete wage as an example, education and experience. Let's consider a wage model where y is wage and x1 is education, x2 is experience. So both experience and education is affecting wage. The coefficient of education is interpreted as the wage associated with one additional year of schooling. So if you, in education now, one extra year of schooling can affect wage, right? Likewise, the coefficient of experience is interpreted as wage change associated with one additional year of experience. So one more year of experience affects wage. This same experience or same education condition is practical meaning of ceteris paribus. So if you are estimating education effect on wages, you hold experience constant. If you're estimating education on wage, you hold education constant. If you are doing experience on wages rather, then you hold education constant. Now let's look at omitted variables bias. Why multiple regression matters. Suppose the true model is this. If we mistakenly estimate a simple regression, omitting x2, the estimated effect of x1 is generally biased because x1 and x2 are correlated, and x2 also affects y. Then there's biased direction intuition. There's multiple regression reduces omitted variable biases by including important determinants directly, but only if the included variables appropriately capture omitted influences. Let's look at inference in multiple regression, t-test and confidence intervals. This is the formula. After estimating coefficient, econometrics quantify uncertainty. That is, different samples produce different estimates. Standard error measures this sampling variability. A test for Bj, whether the partial is statistically distinguishable from zero, small p-values, indicate evidence against null hypothesis. Confidence intervals provide a wide range of plausible values for a true parameter. Let's look at joint hypothesis, the F-test. This is the equation. The F-test evaluates whether a group of variables is jointly significant. That is, adding them improves the model enough to justify their inclusion. So we are looking at S1, S2, S3 together. We are looking at the significance together. RSSR is the residual sum of squares of the restricted model under your null hypothesis. This is from the unrestricted model, where while Q1 is the number of restrictions. That is how many coefficients are set to 0. F-tests are especially useful for comparing nested models. Now let's look at worked example. This is a wage equation data set. We model wages using two predictors, like I said before, education X1, experience S2. Wages are measured in thousands of currencies. Education and experience are measured in years. The estimated equation is this, for example. Y, that is wage, is equals to 4.6421 plus 0.78787 education plus this experience. This is B1, this is B2. What this means is that holding experience constant, each additional year of education is associated with an wage increase of what? 0.780. So if you increase by 1, if education should increase by 1 year, there's going to be, if education increase by 1 year, there's going to be a change in Y by this. Holding education constant for experience, each additional year of experience is associated with what? 0.336 in units, right? That is for this. Good. Now let's look at a worked example here. Interpreting standard errors. The regression outputs, which measures the precision of each coefficient estimate. Larger standard errors imply greater uncertainty. In the example, where you have education, SE is equals to 1.6, and experience is equals to SE is equals to, and all of that, right? Okay. Let's look at a work example, right? Let's look at model fit and degrees of freedom. Model fit summarizes how much of wage variations is explained by the predictors. R squared is equals to this. This indicates, when R squared is this, it indicates that 82% of sample wage variation is explained by education and the experience through the fitted model. That's what this means, if R squared is this. The degrees of freedom in multiple regressions is given by this. With n equals to 18 and k is equals to 2, df is 15. This matters for inference because critical values depend on df. Remember, strong fit does not guarantee correct specification or causality. It only describes explanatory power in sample. Now, this is a diagrammatic representation of actual versus predicted wage. Let's look at multicollinearity, definition, and why it matters. This means two or more regressors are strongly linearly related. It matters because it becomes difficult to separate individual effects from others. Now let's look at detecting multicollinearity. These are the steps. You pairwise correlation matrix among regressor, then you carry out variance inflation factor, then you carry out instability size. Now let's look at variance inflation factor, VIF. This is the formula. I already explained these things before. R squared J is obtained from all this. Then let's look at the work example. A VIV table. Let's look at the interpretation. Now let's suppose the auxiliary regression yield is this, and R squared is this. Then VIF is this, giving this formula. Indicating what? Severe multicollinearity. I already explained multicollinearity before. This means that two or more regressors are strongly linearly related. Now, this is a visual representation of multicollinearity. This is how it looks like. Now let's look at consequences of multicollinearity. What changes versus what does not? What does not automatically change is OLS unbiasedness. What does change is variance and standard errors. If they increase, confidence intervals widen and t-tests lose power. Confidence can also be sensitive to small data or specification changes. Let's look at solutions. You drop redundant variables when they are redundant for the research questions. You combine correlated variables. Each theory suggests they measure the same underlying concepts. Collect more data and seek more variations that break the correlation structure. Always explain your choice. Let's look at model selection. Let's look at the difference between fit and parsimony. Model selection is choosing which variable to include. Economists should guide model selection first, and statistics should support the choice. Two competing goals. Goodness of fit and parsimony, which is simplicity. Adding variables often improves in sample fit, but can overfit and reduce interpretability. AIC and BIC are information criteria that balance fit against complexity. F-test help compare nested models by testing whether additional variables jointly improve the model. Let's properly look at what is AIC and BIC. This is the information. L here is the likelihood of the model given the data, while K is the number of estimated parameters, N is sample size. Both criteria, both of them, prefer smaller values. AIC penalizes complexity by 2 parameters, while BSC penalizes by next billion N per parameter. Use AIC or BIC to compare candidate models estimated on the same dataset with the same dependent variable. Do not compare different Y variables. Let's look at nested model comparison using F-test. When one model is restricted version of another, that is nested, an F-test provides an hypothesis testing approach. Do the additional variables jointly matter? The F statistics compare the restricted model ROSS to unrestricted model ROSS. This approach complements AIC-BIC because if F-tests hypothesis driven for nested model, then AIC-BIC compares model more broadly using fits and penalty. Let's look at a worked example. This is a restricted model. This is an unrestricted model. The restricted model has an omit experience, right? Why the unrestricted has an error term. Given ROSS that is restricted is this. Adding experience using ROSS by what? This. The computed F statistics for Q1 restriction is F is equals to 9.667. If S exceeds this critical value or p-value is small, experience has significant explanatory power and should be included. Let's look at what dummy variables are. Many economic variables are categorical, gender, region, and all of that. Regression requires numerical variables, so we represent categories by dummy variables. A dummy variable takes value 1 or that's what dummy is, either 1 or 0. That's what example, female can be 1. If female is 1, then male is 0. In a wage regression, the female coefficient measures the average weight differences between females and the reference group, that is males, holding other regressors constant. Let's look at an example of this. Wage is this formula. B1 is return to education holding gender constant. B2 is the wage difference between females and males holding education constant. And the important thing here is that B2 is a partial difference. It answers among workers with the same education. How do wage differ? Now let's look at dummy variable trap. If a category variable has M and all of that, okay, we'll look at it better in the next slide. Interaction effect. When one effect depends on another. An interaction term allows the effect of one variable to depend on another. In economics, heterogeneous effects are common. Returns to education may differ by gender. The price effect may differ by income group. Policy effect may differ before and after reform. An interaction is formed by multiplying variables. This creates group-specific slopes. Now let's look at interaction model. This is an example of interaction model. You can see the only difference is that education is now multiplying female. Now let's look at a worked example. Assume all my betas are this. Then females have a lower intercept, but a higher return to education. Because B2 here is less than 0. For education, B3 here is greater than 0. Interpretation, the wage gap may shrink as education rises. The wage gap may shrink as education rises, but female gain more per additional year of education in this specific. That is given this here. This is what we used. Now, this is a diagrammatic representation of the interaction illustration. Now, by way of conclusion, multiple linear regression extends simple regression by allowing several predictors to jointly explain a dependent variable. Its central contribution is the estimation of partial effect, which aligns closely with economic reasoning and helps reduce omitted variable bias. OLS estimation in multiple regression is naturally expressed in matrix form, and statistical inference rely on standard errors, t-test and f-test. However, multiple regression introduce practical challenges. Multicollinearity can inflame standard errors and make individual effects difficult to isolate. Model selection requires balancing fit and simplicity tools using AIC and BIC and nested model F test while still respecting economic theory. Finally, categorical variables and heterogeneous effects are handled through dummy variables, interaction, and terms, which require careful interpretation. Strong empirical work combines correct model specification, credible assumption, clear interpretation, and diagnostic reason. That will be all for module 3. I'll see you in module 4.